As we continue looking at simple harmonic motion and harmonic oscillators, we now turn to waves and vibrations. Right? Waves and vibrations, right? The rationale behind that harmonic motion is waves follow an oscillatory pattern as long as they're given the right conditions. And we see very similar traits in waves as we do in mass spring systems and as we do in pendulums, specifically in terms of their repeating motion. Because at the end of the day, that's what a harmonic oscillator is. It's something that repeats its motion over and over and over. Waves can do that under the right context. All right, so ultimately, what is a wave? Right? What is a wave? How do we define a wave? A wave is a disturbance, right? Somehow there is a disturbance that was caused in some system, which is now causing an imbalance, right? And that that imbalance is going to allow us to transfer energy, right, without changing whatever medium it moves through. Here's the ridiculous part about that last statement. When you talk, right, you are causing a disturbance in the air, which is caused by the vibration of your vocal cords, right? So the pattern that your vocal cords are vibrating with, it takes the air and causes that to vibrate in the same pattern. So as it leaves and enters, right, the greater surrounding area of your face, it continues to have that disturbance propagate through the air until it reaches your eardrum and it causes your eardrum to vibrate at that same pattern. Right? That's your basics on how we hear. Right? Vibration here causes the air to vibrate, causes your eardrum to vibrate in that same pattern, so we get sound. Right? That is our basic sound production. So we're giving some parts of the air energy as a result, right? Because those particles are coming into contact with each other. So we get an energy transfer through contact, right? Through collisions that we see. Without changing whatever medium it moves through. So basically, when you talk in air, it's not like the air becomes water. Or when a wave is moving through water, oh, we see this disturbance of energy, this transfer of energy, and now the water has become chocolate sauce. No, like that's not what happens, right? So the medium itself is unchanged. It's just the particles in there are going to move a little bit as a result of that energy transfer. So based on how we produce waves, we have two different categories that we look at. We have mechanical waves and we have electromagnetic waves. Mechanical waves, right? It's how those particles are going to interact, right? Mechanical waves require particle-to-particle interaction. This is why there is no sound in space, because the particles that exist there are so spread out that those particles don't collide. Right? So you need that particle-to-particle collision, that interaction between them, in order for a mechanical wave to operate. Right? So sound counts as this, water waves count as this. Sound needs a medium, water waves need a medium in which to move through. So mechanical waves do not operate in a vacuum. They need something to go through. Electromagnetic waves, on the other hand, don't require any particle-to-particle interaction. Right? These waves can propagate through a vacuum. Right? So we look at the entire electromagnetic spectrum, right? From radio waves down to gamma radiation, all of those can propagate without having a medium. Can they propagate through substances? Absolutely they can. I mean, think about it. When we see light, that light is traveling through air. That air is full of particles, right? So the electromagnetic waves can travel through mediums that have particles present. They can also travel through when there is no particles present as well, such as a vacuum. And again, by a vacuum, we do not mean a Dyson or a Bissell or whatever you're using to hopefully do chores. It is the complete lack of substance, right? That's what we define as our vacuum, right? So radio waves, X-rays, visible light, all the entire EM spectrum falls under that category. And we have two types of waves that we look at, right? And the way that we define these types are how the vibrations occur, right? And how the wave physically moves, right? So a transverse wave, if you look at the animation here, this is your very typical wave appearance, right? So when you draw a sine wave or a cosine wave, right, you're going to get that up and down, right? You're going to get this pattern here, right? That constant up and down. The word transverse simply means perpendicular, right? So if you look at that simulation, the wave is traveling from left to right, but the amplitude is working vertically, right? So it's moving from the left side to the right side, but it's causing the disturbance to make the spring move up and down, which means that the wave itself, the vibration is perpendicular to the direction that the wave is moving, right? And we can see that through this simulation here. Longitudinal waves are the next type of wave type, and again, it's based on the creation of that vibration. So if you look at your longitudinal wave here, right, this is more of a compression, right? When we talk about longitudinal waves, oftentimes I'll refer to them as a compression wave, because if you notice, the waves themselves are moving parallel to the vibration, right? So the vibrational pattern that causes the wave along the spring is parallel to the spring itself, which means that wave will move parallel to the spring as well. So we don't see any vertical motion here, right? Rather, we see an area of high density and an area of low density. And if you watch as that wave moves along the spring, you see high density, and then what directly follows before equilibrium is established again is an area of low density, right? So you see normal density, you see high density, then you see low density, and eventually that spring evens itself back out, right? And the transverse did that as well. If we go back here, right, the transverse did that too, right? Where we see eventually the medium gets itself back to equilibrium, right? That spring gets back to where it was, right, where we don't see that wave pattern present. Longitudinal does the same thing. Now, as we define the wave terms, right, and the different parts, our displacement of a transverse wave is going to be vertically, right, as we look at it. So again, this is a very classic look at a sine or a cosine wave. The wavelength being measured from crest to crest or trough to trough. You can also call it peak to peak. Really, in order to have a full wavelength, it needs to complete one full cycle. Thus, why it fits in with our harmonic oscillators, right? One full cycle has to be completed in order for a wavelength to be measured, right? And our wavelength is defined by the Greek letter lambda. Here we see the amplitude, right? The amplitude would be the measurement from its standard position to where that crest or trough happens to be, right? That's going to be the amplitude. That's going to be the vertical size of that wave. All right, a couple examples here. Light operates in this way. The secondary waves of an earthquake operate in this way, right? Just a couple different examples of these wave types. Longitudinal waves, right, are a little bit different here, right? Where we see an area of high compression, that is in the direct middle of the picture here. And then we have what's known as a rarefaction. The rarefaction, that is the area of low density. So our compression is high density, our rarefaction is low density. The way that we define a wavelength for longitudinal is compression to compression. That becomes easier to measure than rarefaction to rarefaction. Could you measure that? Absolutely. It's just harder. It's just harder to pick where is the middle of that rarefaction versus a compression. Those particles are going to be so tightly packed, it's going to be easier to see where they're compressed here, where they're compressed there to make that measurement. Right? And what's nice about the way that the longitudinal wave works is you notice the movement of air molecules here. It's both left and right because these particles are going to bump into each other and then they're going to go back to where they were. Right? So they're going to kind of go left to right here as that energy is transferred. Unlike a transverse wave, right, we're going to see that wave, right, that those objects are going to move, that water is going to continue to move with it. Here, the air molecules don't. They shift and then they go back. Then they shift and then they go back. Right? That's what we see for a longitudinal wave. So folks, there are your basics on your waves, your wave types, your wave terminology, which will help moving forward.